In this lecture, we will cover first part of chapter 19 of the S.C. Verma book, Physics Part 2, Physics. We will cover electric field and potential, Coulombs Law, electric field, and so on and so forth. So let's start with the Coulombs Law, which is the most basic law governing the force between two charged particles. Let's say you have two charges Q1 and Q2 that are separated by a distance r, and the force between these two charges F is given by a constant, and this constant is written as 1 upon 4 pi epsilon 0 multiplied by Q1 Q2 divided by r square. The value of this whole constant 1 upon 4 pi epsilon 0 is 9 into 10 to the power of 9, and that figure is easy to remember, 9 and 9 here, 9 into 10 to the power of 9. If you individually try to remember epsilon 0, it's going to be a little hard, so we'll leave it here. The unit of this whole thing is going to be Newton multiplied by meter square divided by Coulomb square. The Coulomb is the unit of the charge. Few things here you need to know is that the force, the fun thing is this is just giving the magnitude of the force. The force is a vector quantity and it always will have a direction. So if the two charge, similar charge, they repel it, and dissimilar charge they attract. We will need to keep in mind when we need to find the resultant force on a particular charge due to two different charges. It's not just that we can add these two forces and arrive at the total sum of the forces. We need to take into account the direction of these forces. So let's go through some simple problems, and then we will cover more things. So this is we have a question number 6 of this book, which says there are two charges, 2.0 into 10 to the power minus 6 Coulomb and 1 to 10 to the power minus 6 coulombs are placed at a separation of 10 centimeter. Where should we put everything on an axis? It's easy to visualize that way. This let's call it the first charge. We call it 2q. The other charge we call it q, or the amount is q, where q represents 1.0 10 to the power of minus 6 coulombs. And they are separated as a distance r, where r is 10 centimeter. Now the question is, where should a third charge be placed such that it experiences no net force due to these charges? So if you try to place the charge right at the center, then this charge will have a repelling force due to this charge. Let's call it F1, like this, and this in this direction, and this force Q will have a force in this direction. Let's call it F2. Now because this charge is higher in quantity, so it will have this force F1 in this direction will be higher than the force due to this charge in this direction. So if you place right at the center, it will experience a net force in this direction toward the positive x-axis. So in order to balance out these forces, we would want to place this thing right, not in the center but somewhere right to it, and we don't know that distance. Let's call it distance d. So now the force will be higher due to this 2q charge, but because it's at a farther distance, it will be lower due to the distance, because this distance r. This distance will be r minus d. Now let's say on this charge, the force due to this 2q charge is F1, and force due to this q charge is F2. So we need to make sure that F1 is equal to F2. Now F1 is 1 upon 4 pi epsilon 0 multiplied by Q1 into Q2. Let's say this charge has a whatever some other quantity Q. So we have 2Q into capital Q divided by distance d square should be equal to this force F2 is the force due to this one. So 1 upon 4 pi epsilon 0 multiplied by Q1 is Q, Q2 is capital Q divided by the distance between these two, R minus D whole square. Cancel out 1 upon 4 pi epsilon 0, 2Q, Q into Q, Q into Q go away, and then we take this one upside here. So we have 2 multiplied by R minus D whole square is equal to D square. Expand this, we get 2R square plus 2D square minus D square is D square minus 2RD multiplied by 2 is 4RD. We need to solve this equation for D. What we do is we take a ratio of D by R, divide whole thing by D square, so D square by R square, so D by R is D by R whole square plus 2 is R square divided by R square minus 4D by R. You can rearrange this, D by R whole square minus 4D by R plus 2 equal to 0. You can solve for D by R as minus B plus minus square root of B square minus 4 into A into C divided by 2 into A. This gives us this minus B is minus 4, so it's plus. So D by R is 2 plus minus, this is 8, which is 2 square root of 2, and 2 is cancelled, so we get D by R as 2 plus minus 2. D cannot be more than R, so we reject 2 plus square root of 2. So the only solution is 2 minus square root of 2. You should always remember square root 2 value, which is 2 minus 1.41 or 0.59. So D is going to be R multiplied by 0.59. R is 10 centimeter, so it's 5.9 centimeter. So we see that the force has a direction, and in this equation it's simple that it's only on the x-axis, so we only need to take into account plus and minus. But in general, force can have any direction x, y, and then we need to resolve it into x-axis and y-axis. We have another problem, question number 7 in the same exercise. Suppose the second charge in the previous problem is minus 1 into 10 to the power minus 6. Locate the position where a third charge will not experience a net force. So we have a 2Q charge here and a minus Q charge here. We need to find out where do we place a third charge in such a way that it does not experience any net force. So this is x-axis, and let's speculate we need to place it. We want to place it somewhere here, let's say in between, and we're trying to balance it out. Obviously this is not going to work, because if it's a plus Q charge here, this is going to have a force of attraction due to this charge, and this will have a force of repulsion due to this charge, both of them acting in the same direction. So it will experience a net force in this direction. It can possibly be here, or it can be here. And let's say it's at a distance r. We place a charge capital Q right here, and we are speculating that this is a higher charge, so this will have a force of repulsion in this direction, F1. So this force is higher because of this charge, but Lower because of this increased distance r compared to q. Because we know this distance, we call it, let's say, distance d, and we call it distance r. R is known, and we need to find out the distance d. So this distance becomes r plus d minus r. So we need to find out f1, and under what condition f1 becomes equal to f2. So F1 is the force on this capital Q due to this charge Q, capital 2Q, this is charge capital TQ, and it's given by 1 upon 4 pi epsilon 0 multiplied by first charge 2Q multiplied by the second charge Q divided by the distance between them, which is D. And this should be equal to force F2, which is the force on this particle due to this negative Q charge. So we get 1 upon 4 pi epsilon 0 multiplied by Q to capital Q divided by D minus R whole square. So we cancel out this, cancel out Q and Q, becomes 2 into D minus R whole square is equal to D square. If you simplify is, we get 2d square minus d square is d square minus 4rd plus 2r square is equal to 0. We need to solve it for d, so we get it d by r whole square minus 4 into d by r and then plus 2 equal to 0. We solve d by r is equal to minus b plus minus square root of b square minus 4ac divided by 2a. So d by r becomes 2 plus minus square root of 2. Now d cannot be less than 1. So we reject the negative one, we get d is equal to 2 plus square root of 2 multiplied by r. You can substitute and then multiply it by 10 centimeter, you get the numerical value, which is 3.41 multiplied by 10, or 34.1 centimeter. So these are the simpler problems of Coulombs law. To recap, we need to remember this formula: force is equal to 1 upon 4 pi epsilon 0 Q1 Q2 divided by r square. And then you need to remember the 1 upon 4 pi epsilon 0 is 9 into 10 to the power 9 Newton per meter square. Force is a vector quantity, so this is only reflecting the quantity of the force. You need to always remember that force is a vector quantity. If it's a simple system for two, it's just the direction is either the attraction or the repulsion. But if you have a multiple particles in a lying in a geometrical fashion, you need to calculate the direction as well. So we'll look at some of those complicated problems in the next series. Another thing you need to keep in mind that the charge on electron is 1.6 into 10 to the power of minus 19, and all charges are a multiple of the charge on an electron. Or since the proton also has a chain charge, electron has a negative charge, protons have positive charge. So any charge is going to be a multiple of these charges. You can go through all the problems in the S.C. Verma book. In the next lecture, we will look at the electric potentials and other things.